Okay, so we have been discussing about approximate inference. This is what we discussed earlier, that we have a distribution. The original distribution is a non-standard one, and how do we use it effectively? So what we said, that we can approximate it with another distribution which is easy to use, right? And we said that, okay, we have our P star, which is um, a, a difficult, or which is a non-standard distribution, and then we can approximate it. So to approximate it, we need a family. So let's say our family of distributions from where we want to estimate our approximate distribution is this capital Q. Now this capital Q can be parameterized by several number of parameters. For example, if it is a Gaussian family, then we know that mu and sigma are the parameters. And if it is a Gaussian mixture model, then we can have multiple of these Gaussians coming together in a weighted sum fashion to create this family of distributions. And now our goal is to find the Q from this family, capital Q, such that this Q is closest to P star in some sense. So what is that sense? We said we can take KL divergence as that distance metric, that we want to minimize the KL divergence between the the non-standard distribution P star and our family Q, which we know how to use easily. So once we find out our Q, then we can use Q for various purposes. So this is the whole thing, and we said, yeah, KL divergence is a simple thing. And yeah, then we came to a very interesting model called Ising model, because we want to see what are the uses of such approximate inference. And Ising model is a very uh, complicated in the sense that it is very high dimensional PDF. So it is like a lattice, and or a grid, or a matrix, where each site can have either a +1 value or a -1 value, and it is interacting with the neighboring sites, the immediate neighbors. And the interaction is driven by statistical mechanics or statistical equations. The energy of the whole lattice is given by this thing, that the product of neighboring sites. So if yi is +1, yj is -1, then the product is -1. And then similarly, you sum over all the neighbors, immediate neighbors, multiplied with some beta term, which is inversely proportional to the temperature in the statistical physics sense. And then there is a negative sign or a positive sign, depending on whether it's a ferromagnet or an uh, antiferromagnet. So what happens is that this is just the energy term, and the distribution, the PDF of this, the joint distribution, is given by Gibbs distribution. Did we discuss that? Yes, it is here. So the PDF of the entire lattice is given by exponential of minus energy of this lattice divided by some normalization constant, which is also called the partition function. And generally, this is very difficult to compute because, so let us say you have a 4x4 lattice, then you have to find all possible values which this lattice can take, right? So let us say all are up, all are down, or first one is up, rest all are down, second one is up, rest all are down. Like how many total states are possible? So total 2 to the power 16 states are possible. So which means so this term is a sum of 2 to the power. So generally, this Z is very difficult to compute, even for a small lattice like 4x4 lattice. Now imagine that if you have a really big lattice, then this term will be really not possible to compute. So that's why uh, we use we leave it as z and we say that we can't compute it. We just try to work with the numerator only. Okay, now the thing is, okay, let me recap. So what we discussed, this is Ising model, which is every lattice site is given by +1 or -1, and the distribution, the joint distribution is given by a Gibbs distribution function. That probability of a state y is exponential of minus energy of that state or energy of that lattice. And this energy is given by this term, which has basically neighboring terms are only interacting. Now, you can see such PDFs are very difficult to work with. First of all, because of the normalization factor, and secondly, also because of that this y term is very complicated, and so it becomes difficult to compute. Now, what we can do is we can use KL divergence to find a let's say, first of all, we assume a family of distributions Q and then find the distribution from that family which is closest to this distribution. And the advantage is that that family of distributions is easier to work with. So one such family is like this, where we assume that each dimension is independent. See, each dimension is independent. Okay, so this is the kind of distribution which we assume, and it's easy to work with, right? How it is easy? Because since each dimension is independent, you can factorize it in this way, right? The joint distribution can be factorized in this way, and then this factorized distribution is very easy to work with. Like if I ask you, can you draw uh, the dependency graph, the graphical model? How do you represent it? So the graphical model will be like each individual nodes. Like there are no dependencies. Every node is independent, right? So it's very easy to work with. So okay, now, but remember that this is an approximation. This is not the exact distribution. This is an approximation. And we saw an example. Let's say you talk of a Gaussian distribution where the two dimensions are correlated, but using mean field approximation, you will assume that they are uncorrelated, that they are both independent. I think independence is a stronger condition rather than just uncorrelated. So they're independent. And then we can approximate this blue distribution, which is the approximate distribution, and where the white one was the original one. So you see in the blue distribution, there is no tilt. The tilt won't be there because the tilt term is there because of Z1 and Z2 interacting. And since our PDF, in our joint PDF, both are independent, so we don't have that tilt thing. And we saw that the advantage we get is, first of all, yes, we are able to get rid of a complicated sigma matrix, and we are just able to work with a diagonal matrix composed of small sigmas. And secondly, also this is our number of parameters are reduced. And then secondly, our form has been simplified to just product of univariate Gaussians. So our form has become simplified. So for any analytical analysis, analytical study, our PDF has been simplified. So this is what we discussed last time. Now, today we are going to discuss about how do we approximate. Can we find a general form for mean field approximation? The answer is yes, because the family of distributions is very convenient, and we can find an analytical simplification to, given any joint distribution, we can use mean field approximation to find the independent distributions. So let us start with the derivation. The derivation goes like this. Okay, so the goal is, okay, first of all, let us start with, okay, So the goal is that we are given a P star Z. Right? Where my P star Z is this is small z, and this is composed, this P star Z, where basically this is equal to, here you have Z1 comma Z2, right? Comma so on, right? So this is a joint distribution. And we want to approximate it. Approximate it with a QZ which is basically equal to product. It's a factorized distribution, or each dimension is independent, QZI. And here you can say, instead of saying ZI, I can simply say this is QI, right? I mean, this is just a I equal to whatever is the number, 1, 2, whatever, basically. So I think this is obvious. I'll just put I here, right? So this is my goal, right? So we have to find QZ. Now the process is, so this is the goal. And what is the method? So the overall overview, you know that we have to find the Q by minimizing the KL divergence between QI, or basically Q capital Z, and P of capital Z. And you have to minimize over Q. Right? You want to minimize this KL divergence and find a suitable QZ. So this is the principle. And okay, and it turns out that minimizing it all at once is a little difficult. So in optimization, there is a very popular algorithm called coordinate descent algorithm. Coordinate descent. So we will use coordinate descent. So what does this mean? It means so one very easy solution would have been, you just find out this function, differentiate it with respect to QZ, and find out the minimum with your simple, you know that at the minimum your derivative is 0, right? Find the derivative, make it equal to 0, and you get the answer. But you know, Z is multidimensional. It is difficult to do it that way. So what does coordinate descent say? It says that instead of optimizing for all the parameters at once, you do it successively. You first minimize over one particular coordinate, and then go to the next coordinate and optimize it with respect to that coordinate in that way. So which means you do, so step 1, you say my Q1 is equal to minimum of Q1 KL divergence of Q star, Q and P star, right? You minimize only over Q1. Step 2, so you use this Q1 and update your Q, and you say my Q2 is now minimum with respect to Q2 KL divergence between Q and P star. This Q is updated now, actually. So basically after this you say Q is this Q1. Okay.
Sir, will it be min or argmin, sir?
Yeah, good point, Argmin. Thank you. So you first minimize over Q1 up. I will just say update Q. I will not confuse you with too many notations. Update Q. Then again update Q. And this way you keep on doing it, and after some time you repeat. So let's say step of n plus 1 is go back to step 1 until convergence. You have to have some convergence criterion, right? You know that in every machine learning, wherever you use approximate solutions or iterative solutions, you have to have a convergence criterion. In this case, the convergence criterion is okay, my KL divergence is not changing. It has become almost constant, not reducing any further significantly. So like that, you can use some convergence criterion. Or my parameters are not changing. Right? These are usual things. So okay, so we use coordinate descent algorithm to achieve this, right? So let's do again a recap. So we are given a p star z, the Gibbs distribution in the Ising model, for example, or it could be the joint Gaussian multivariate distribution in this case, and we want to approximate it with a QZ where all the z's are assumed independent. And how do I achieve this? I want to find the optimal value of QZ. So optimal function QZ, it's not a value, it's a function QZ. So this is a functional, which means a function of functions. So I want to find an optimal function which minimizes this KL divergence. So this QZ should come from this family, Okay, then the to minimize this KL divergence, the usual descent algorithms or usual analytical solutions are not working or not possible. So what I use is coordinate descent algorithm, where I descend along each coordinate at a time. So descend along one coordinate at a time, then the next coordinate, then the next coordinate. So in this way, I make my optimization problem tractable. So this is the whole thing. Now, how do we actually do it? So to do this, what I will do is let's write down. It's a little messy derivation, so please bear with me and make sure that we don't do any mistakes along the way. So let's first try to optimize it with respect to k. So uh, minimize with respect to qk. Some k can be anything between 0 to n, or sorry, 1 to capital N. Let's say where capital N is the total number of variables in this p star. Okay, then I have to minimize my KL divergence, and I will use some simplified notations. Okay, what is my simplified notations? I will say this thing I will call as QI ZI, or simply QI, right? ZI is obvious, kind of. So this is and I will call this as simply a p star. And I assume, okay, all the things in the subscript and in the bracket, they are obvious because it's the entire joint distribution. So p star denotes that. Okay, so KL divergence between uh, product of QI, right? Right? You remember this? Product over I, all QI, right? And I have to find the KL divergence with respect to p star, right? So I have to minimize this thing with respect to qk. So let's expand this. What exactly is this? So the formula of KL divergence is integration, because these are continuous variables. Assume my z is continuous random variable. Of course, in Ising model, it's a discrete random variable, but in general, if we are doing, it is a continuous random variable in general. For example, in the case of Gaussian distribution, this was a continuous random variable. So, and then what you write? You write this distribution, product over I, QI. and log of this distribution upon this distribution, right? Product over I, Qi divided by P star, right? This whole thing. And you have to integrate it over all the dzi basically. So all the z's is basically you have z1, z2, z3, z4, everything. And because we have put this thing here, so this thing can be written like this. But actually it is, okay, if you want to write it separately, then it's, or just to make it simple, I will just write it as z vector. Okay, this is also equally valid. There is a notation overload. You see, there is an I here and there is an I here. I could have called it J also, but because this I is just locally here, locally here. Okay, so now what we get is, I have to now notice that we want to find only with respect to K. Only K term is important. I will just use another J here so that you don't get confused. This J is different from this I, right? There are two different dummy variables here. Now, I want to minimize, or basically I want to minimize only with respect to K. So let me take out the QK term from all these things. So what this becomes equal to some QK times okay, so I think first we can open it up. We can say this is equal to QK times product over all J such that J is not equal to K. Right? All J takes all the values except K times QJ, right? Times log of, again here same thing, QK term comes out, QK product I all I except K, QI, right? Divided by P star. P star has all the Z times here this was a vector, so I will just take out my kth term dzk, and this is product I not equal to k dzi, right? So and then we have integration, right? This step was simple. We have just taken out the qk terms. Now what we do, we have to separate. Let's say we separate this from this. So this becomes equal to summation over qk, integration qk. Now this log of qk I take out. Log of qk times everything. J is not equal to k qj, right? This term comes, this term comes, and then this term comes. It is equal to d zk times okay, let's write the whole thing since we have already broken it up. I is not equal to k dzi, right? This term plus the remaining term I will write. So this becomes plus the remaining term is this whole thing comes qk product I not equal to k qi, right, times log of product I not equal to k qi. Oh, it was j or I. Okay, anyways, it's a dummy variable, and I'm putting this bracket to show that the scope of this dummy variable is only within this much p star, right? Anything else left? Then again dzk and product over I not equal to k dzi, and then again an integration here. I've split this into two parts. Now consider this term. Now qk zk, qk zk is here, qk zk is here, and these terms are independent of zk, right? So basically this and this go together, while this and this go together. But you know what is this? Integration of qj or qi and summation over all the z's, right? Basically, and you know that summation over of any qj times dzj, uh, and product over all j not equal to k, right? And you know this thing is 1. I should have drawn it with green. Okay, let me see if I can convert it into green. Yes. This whole thing is equal to 1, right? Integration of probability function over the entire space is just 1, right? So all these terms become 1. So these terms are these terms vanish from our uh, equation, and we get simply this is integration of qk, right, log qk times dzk, right? This term is simply this. Now let's look at the other term. What becomes of the other term? Uh, in the other term, uh, let's try to separate the variables. So you see dzk is here and qk is here. These terms have no zk. This term has no zk. Here the denominator will have zk. Let's try to separate it also. Let's try to separate that also. So how do we separate? We say plus integration of qk pi I not equal to k qi times log of pi, this was not equal to k, I not equal to k qi times dzk dzi and product of I not equal to k, right? And minus integration of, and same thing, qk pi I not equal to k qi. I'm writing like everything in detail so that you easily are able to follow. Log of p star times dzk and I not equal to k dzi. Okay, I think we have written all the terms properly. Now let's look at these terms. So here we have got qk, and these are all qi dzk. Now see integration, because this integral can be split, and you know this integration of qk dzk is simply equal to 1, right? So this and this vanish, and only these terms remain. But now you notice that these terms and this term are independent of k, independent of zk or qk, independent of qk, right? And you know originally what we are doing, we are minimizing with respect to the function qk, and these terms are independent of the function qk, so means these terms are simply constant, right? So this whole term is simply a constant. Oops. Constant with respect to qk, right? So it will not play any role in my optimization. Now let's come to this term. Let's examine this term again. Here we cannot reduce because this p star also contains zk, right? So we cannot reduce this. Uh, it's qk, dzk, and these terms. So, okay, let's try to write this in a clever way. So let me start the equation all over again. This is simply equal to qk log qk times dzk integration plus some constant. I will not bother to write that again because it's not playing any role in our optimization. Minus, now we are writing this term again. So this term can be written as qk integration times, now this is integration of pi I not equal to k qi times p star. So basically it has got all the z's. P star has got all the z's times d z
Log P star.
dzi dzi, and where I is basically not equal to k. Right? And I put
So
this
it will be log P star.
log p star. I'm sorry, log p star. And then outside is this dzk. Right? I've just grouped together these terms and taken this integration like this. So now what is this term? So this term is simply, uh, this can be written as expected value over q of minus k times log of, I mean, expected value of log of p star, right? Now, what is this q of minus k? Q of minus k is basically, uh, q of minus k is basically product I not equal to k qi, right? Means qi zi, or simply qi is sufficient because we have already defined that notation in this way. So this is sufficient to write. So what is the meaning of x? So if in case you are little unfamiliar with this expected value notation, whenever we say expected value over some probability distribution p of some function of z, this is equal to integration of fz pz bz, and this z can be vector or scalar, anything, doesn't matter. All right, you can write it as pz. Expected value over some pz of a function fz, it is simply fz times pz times dz integration over all z. Oh, why did I put brackets? Okay, that's it. So this is the meaning of this term, expected value of. So since our distribution, the PDF is simply this product of all qi except qk, all I except k. We call that as q of minus k, the whole joint distribution as q of minus k. It's a joint distribution of all variables zi except zk, right? And you know, in the q family, they are all what do you say? They are all independent. So which is, so it is this thing simply, right? So I think this part is clear. Now, of course, this whole thing can again be written as expected value over qk of this function, because this function has a zk somewhere in this, right? Zk is there. So that's it. So, okay, now let's try to combine these two terms. See, this is qk dzk, qk dzk. So this part and this part can be combined. How? Is log of q, and this can also be written as log of something, log of exponential of this thing, right? So this becomes simply equal to integration qk log of qk upon, this is I have to now bring it within the log, so it becomes exponential of uh, e q of minus k log of p star times dzk plus some constant, right? So now what is this? What is this? This term is the KL divergence between QK and this new term. Constant part anyways is not important. We are not concerned about it. This is simply KL divergence between QK and e to the power q of minus k log of p star. It's again a KL divergence. Now, to minimize this KL divergence, I have to minimize this KL divergence. This is just QK is a single random variable, or a univariate random variable. Now, what is this minimum of this? What is the minimization of this? What is the minimum value of QK now? What value of QK minimizes this KL divergence? Anybody can write on the chat window. So KL divergence between two PDFs is minimum when the two PDFs are
the same.
or are equal. So this means this minimum is achieved when QK is equal to, so this KL divergence is minimum when QK is e to the power exponential of q minus k log of p star. This QK is a PDF, and this part is not a PDF because it's not normalized. So you have to multiply it with some constant, right? Or divide it with some z to make it normalized. But this is the unnormalized form. And we have discussed that for practical cases, the numerator itself is sufficient and the normalization constant may be left as an unknown term. Basically divide by some z, some normalization constant, right? So that's it. So basically we are able to, with the help of this formula, we can approximate any joint distribution using mean field approximation, right? So you apply this formula to your Gaussian distribution, the joint Gaussian, and you will get the values of this mu I, sigma I, etc., which is basically which will give you a PDF from this family of distributions to approximate your original PDF, right? It was an easy derivation, but just that since we have so many terms, so we were kind of stuck. Okay, now the thing is, this is coordinate descent algorithm, so you have to do it for every k. So you start with the first lattice site or the first random variable, find this out, then go to the second random variable, find this out, and as you are doing it, your overall Q is getting improved and improved, and ultimately you'll be able to achieve the best possible answer. Okay, now we have to apply it. We can see one example of applying it to the Ising model. So let's say I will define my Ising model again. Applying mean field approximation. To Ising model. So basically, let's highlight that this is the final result of all my approximation efforts. And this has to be done for all k. Basically, you have to do it one by one in a coordinate descent fashion. Okay, so what is the Ising model? Ising model is, as you know, you have sites and each site can have +1 or -1, and your probability of the entire site is given by, or I would say Py of your vector y. Py of vector y is given by exponential of, you remember, I think it was plus beta or minus beta. I think it was a plus beta because E was minus beta and this is minus of E, so it becomes plus beta. Yes. So there is a constant beta times summation over all the neighbors I comma j, right? All the neighbors I comma j, yi and yj. There is a change of notation. Instead of z now we are using y, but that is a small thing. That's it. This is the thing. Now, this is the normalizing model without any external field. If you apply an external field, then you get an extra term. So where bi is some external field and your yi is the value at a particular ith location, and you sum over all I. So this extra term is basically because of an external field. External field Pi at the lattice site I. Right? Because the field can have different values at different lattice sites. So we are doing it in this way. Now we can see that this is a very complicated distribution. How do we approximate it using using mean field approximation? So in mean field approximation, I will simply say my P of y is simply equal to qi yi, and they are just all independent. So my I is varying from 1 to 16 in this case, or 1 to n in general for any n sites in the lattice. Now, what happens is, let us apply the result of mean field approximation. What is the result? So this was the result. And let us see what is my log of qk. Means it's exponentials. I will just work with this term. So my qk is basically, or my log of qk. So this is using mean field approximation. So my log of qk is equal to expected value of q minus k, right? This is simply the formula which we read, log of p star. So p star is here, p of y, right? My p star is simply, let us plug in the values. So this is expected value of q minus k log of py is, what is py? Py is this. So log of py is, okay, it's easy to handle here because it's exponential thing. So log and exponential go away. So it's simply beta times summation over all the neighbors, I comma j, and qi qj, or was it qi qj or yi yj? I'm sorry, this is not the distribution but the value of the random variable vi yj plus some b I yi summation over all I, right? So that's the thing. Okay, but now you notice one thing. That we want to find the what do you say, expected value or the average over all the lattice sites except the kth lattice site. So when you take expectation over, so you remember that you have, let us say, these lattice sites, and you have these lattice sites, another lattice sites are also there. Let us say this is my k. If this is my k, then this term, this term, this term, and this term, only 4 neighbors are uh, affected, and rest everything is independent of k, right? These terms are independent of k, independent of yk, right? These are independent because here they will not appear together. They can be factorized even within p also. They are not dependent on k, the value of the k. So what we can do is, when we take the expectation, all those terms, these terms are simply averaged out, right? Because they are not so they simply, the expectation value over these terms will just simply take them away. So so they will be simply constant with respect to k. So basically this is equal to expected value of q of minus k beta summation over I comma k, right? Yi yk. So just a minute, I will. So basically what we are doing is, in this summation we are only considering these 4 links. Only these 4 links are considered. So I will say summation over k comma j. It could be anything, I or j. I have simply chosen j so that here I'm putting my I equal to k. I'm simply putting my I equal to k. Yk yj plus summation over I also. I is simply j. So I is simply k. So bk yk. Right? All other terms are simply gone and they are independent of constant with respect to yk, right? Those terms don't contain yk, right? So now let's try to look at this term. So this term is simply, okay, I have to open it up, beta. So see, expectation value can go inside, summation over all k comma j, all the neighbors of k basically, and expectation of, now see yk, this distribution does not have k, this does not have qk, right? So yk is simply a constant with respect to this distribution, so yk can come out, and yj, the random variable yj is contained in this joint distribution, so this will be simply an expectation value over yj. Okay. And here I can say this is q of minus k, which basically it is simply q of j, right? Where j is the neighbor. What do you say? I can simply say this is q of j, right? Plus bk, yk. And these terms again are independent of q of minus k, right? Q of minus k does not affect these terms. That's it. So plus some constant which leave. Now this term is uh, simply, we call it as mu j, right? It's simply the mean of pi j. It's simply the mean term. So we call it as mu j. Now what does this become? So now this is equal to this is yk times beta summation over all j equal to neighbor of k, right? This I can say mu j plus vk, and yk has been taken out as common, right? Plus some constant which we are not concerned with. Now this term is, see, this term is independent of the value of yk. It just depends on the neighbors of yk. I call it as m. I can call it as mk also, but I call it as m. This basically, it depends on the neighbors of yk, neighbors of k. It just depends on the neighbors of k. So my q takes a very interesting form, that my qk is basically simply exponential of yk times some constant, right? My q is very simplified. My qk is simply exponential of yk mk, and times some constant upon some z, some, you can call it as zk or something, some constant z. Now to find the value of this constant, let me call it as the constant as some c, my, and now I can find the value of c, right? Because I know yk can take only two values, plus 1 or minus 1, so I can find the value of c. So how do I find? By normalizing it. So if I normalize, it means my, when my qk, when my yk equal to plus 1, plus qk when my yk is equal to minus 1, this should be equal to 1, right? So which means my c of e to the power mk, or I will just write it as m, plus c times e to the power minus m is equal to 1. So what is the value of c? C is simply 1 upon exponential of m plus exponential of minus m. So this implies my qk is simply exponential of m and you know what is this? This term is simply okay, let us say, what is my qk when my yk equal to plus 1? This is equal to e to the power m upon e to the power m plus e to the power minus m. This is equal to 1 upon 1 plus e to the power minus 2m. This is an sigmoidal of 2m, or you can say 2mk, whatever. So that's it. So this is the thing. This is simply the sigmoidal of 2m. Now we can also find out what is the value of mu k here. This was a mu j is simply exponential of mu j is simply, my mu k is simply expected value of qk. Did I write it correctly? Oh, sorry, expected value of yk. Expectation qk yk, right? or j or k, anyways, it doesn't matter. So mu k is simply, what is this? So yj times, basically, what do you say, c times exponential of plus 1 m plus minus 1 times c times exponential of minus 1. With now put the value of c here, so you get exponential of m plus exponential of minus m divided by, sorry, minus sign here, divided by exponential of m plus exponential of minus m. This is simply tan hyperbolic of m. You can call it as mk. That is the value of mu k. So in this way, you see, you have simplified your very complicated distribution into a simpler to use distribution. This is called approximate inference. Okay, I think a lot of exercise involved here. But what is the utility of doing this? This I'll be showing in um, today's lecture or also in the next lecture. So the utility is that we are able to use, we are able to express our complicated distribution in terms of simpler distributions. Okay, anybody has any questions here? Otherwise, I will start a new topic.
So just a little above, little more. Okay, quite a bit has been done. More. Yes, sir. Here P of I. The P of I next to lattice. Yes. There would be a partition function as well, right?
Yeah, good point. Thank you. Yes, there is a partition function also. Very well noted. There is a partition function here z. And
So how would, I think I should have asked it before. It would carry on, right?
no, it is constant with respect to yk. No? So it will just merge with this constant term.
Oh,
So this is this thing divided by some z, right? So this is, we have taken a log, right? So this is minus log z, right? Minus log z, and this log z was a constant with respect to yk, right?
partition function was the summation over all yi's, right?
Yes, but it is constant with respect to individual values, right? Because
Yes, yes.
we have summed over all possible values of yi. When yi is plus 1, yi is minus 1, etc., etc. So all those values have been summed up. So there is no random variable left. So, is it clear?
So thank you, sir.
Yeah, thank you. So, okay. Was this clear? Okay, then we can move on to the next topic. I will